In this video, we're going to look at why we use high voltages to transmit electric power very long distances. And the reason we need to transmit the power for very long distances is because typically our power plants are far away from the cities or other places that we live in. In my case, I'm near the city of Ottawa, and a lot of the power plants are maybe 300-400 kilometers away, typically clustered around Toronto. And for this example, we're going to pretend we're going to get all our power from the nuclear power plant in Pickering, which is about 300 kilometers or 200 miles away. So what we're going to do is imagine that the power transmission line from here to here is 300 kilometers long, and we'll look at how to model that using resistances, and we'll also look at the voltages that are lost in the resistance in the line and the currents through the line, and we'll try it both at 120 volts, the usual house voltage in North America. If you're in some other part of the world, you could pretend it's 240 volts. It's not going to make a huge difference to the outcome of what we're doing. And when we see how 120 volts low voltage fares for power transmission, we'll then try it using these 10 kilovolt transformers and see if that does any better. And spoiler alert, of course it does, or we wouldn't use high voltage for long distance power transmission. Before I continue, we should talk a little bit about safety, because if there ever was a video where "don't try this at home" applies, well, this is one of them. We're dealing with some significant voltages. These are two 10 kilovolt transformers, and things like that should not be taken lightly. I have years and years of experience with this sort of thing, and even then I'm using all sorts of safety interlocks, such as a dead man switch, which you can look at in one of my previous videos. But I really want to emphasize this is not something to play around with, and the voltages we're dealing with are really quite dangerous. So after building all this equipment, well, let's get on with the experiment. So this is the setup we're going to be using for our high voltage power transmission tests. This side over here is going to be our power station, and because I don't have a thermonuclear plant in my basement, we're going to use this little power adapter to provide, well, 120 volts to our transmission line, and also provide a connection to neutral to the neutral conductor down here. And there you go. It's all set up. So power comes over here, and well, what we'll do is we'll remind ourselves that that's our nuclear power plant with that little photograph over here. And at the other side is home, and we'll remind ourselves of that with this photograph, and home is going to be attached to our power line with this massive cable over here. And we'll also attach neutral to the lamp. And so what we have is our lamp attached to 120 volts. It's a 60 watt lamp, which was very common in the days of incandescent lamps, and it should draw about half an amp, give or take, and we will make sure we can measure it by setting up our volt, or our ammeter I should say, and we'll see if we can set up the ammeter maybe like this so we can see it from the camera. And finally, we should verify using a nice voltmeter what the voltage on our power line is. And we'll do that by attaching our voltmeter leads to the neutral and the live. So here you have a 120 volt power system that would be, well, much like in the days when Thomas Edison did DC power at 100, 120, 110 volts, and you really didn't have any way of increasing the voltage beyond that. So that's our setup, and we should try it. So I'm going to go to the other end of the camera and we'll turn it on and see what happens. Okay, here goes. And what we can see is the voltage on our AC line is 124 volts AC, and the current flowing is 0.43 amps. And actually, that's not bad. It probably means the lamp is drawing a little bit less than 60 watts, but who knows? Those lamps aren't that accurate. And for that matter, as the filaments get older, they get a bit thinner and the lamp uses a bit less power. So that is the most basic setup. So that was a nice little demonstration, but it's not very realistic. Usually our home is considerably further away from the power station than, well, 1.5 feet. In fact, for the purposes of this demonstration, we're going to say most of our power comes from the Pickering Nuclear Power Plant, shown there, and it's on the shore of Lake Ontario near Toronto, and I'm near Ottawa, and that's a distance of about 300 kilometers or 200 miles. And because of that, suddenly the cable itself, the wire itself, has a certain electrical resistance, and that resistance becomes quite significant. Now, for real power lines, the cables are quite thick, as you would expect. They're carrying hundreds or thousands of amps, but that's not very meaningful to you or me. So instead, what we're going to do is say the Electromagnetic Videos power company is going to use some extension cords to go from here to the Pickering nuclear plant. And whether the extension cord is sort of a nice fancy one like this or a cheapo lamp cord like this, they typically use number 16 AWG wire in them, and that is, I believe, something like 1.3 millimeter squared type conductor sizes for those of you in Europe and other places that use the metric system. And when you do the calculation and you've looked up the resistivity of the wire, it turns out that if we made our transmission line going to the power plant with the neutral coming back out of number 16 wire, the resistance that wire would have is about 8,000 ohms. Just roughly. It varies considerably based on temperature, based on manufacturer, and so forth. Now, we'd never do that in real life, of course. If we were putting up a power line, we certainly wouldn't use extension cords. But it sort of puts things in perspective. So what I've done is to mimic the 300 kilometers of power lines where we've got 300 kilometers of the live and then 300 kilometers of the neutral wire bringing it back. The 8K in total, in other words, 4K for this and 4K for that, is, well, this string of 1K resistors that I soldered together. And so what I'm going to do is very quickly insert them into the wire, and we're going to use that to mimic what would happen with a real world power line. So bear with me while I do that. All right, so we have our 8K worth of resistors in our power line, and I'm going to add one more voltmeter so we can look at the voltage on the light bulb, and maybe we will attach it here, this is really the voltage at the light bulb, even if it isn't quite where the light bulb connects itself. And I think we're ready to power it up and see what happens. All right, here goes one more time. Well, the light bulb sure isn't very bright. If we look at the voltage on the light bulb, it's about 0.3 of a volt. And if we look at the current on the ammeter on the right, it's about 13 milliamps. And what that essentially says is there is so much resistance in the transmission line that, well, it's limiting the current to be far less than what the lamp would normally consume, and essentially the lamp is getting virtually no power. It's certainly getting some, but just a minuscule amount. The bulk of the power being dissipated is being dissipated in the power line, and even at that, not very much power is being dissipated in the line itself. So we've essentially stopped all power transmission. Well, what can we do about it? What we're going to have to do is increase the voltage on our power line, and that will hopefully get more power through the enormous resistance in our 300 kilometers of wire as simulated by that resistor. And to do that, well, I have these wonderful high voltage transformers, and we will hook them up to provide high voltage power transmission. Okay, I've added in a couple of transformers. This one over here is a step-up transformer. Let's see if we can put the picture somewhere here. It's like the transformers you see on power poles near your home, at least if you're in North America. In other parts of the world, they look a bit different. And we're going to use an identical transformer at the other end of our power line, a step-down transformer. And of course, at this point, I have to tell you what the voltage we're going to use is over our new and improved power system. These are 10 kilovolt transformers, meaning we have 120 volts going in, and we have 10 kilovolts coming out between the hot or live terminal here and the chassis of the transformer, the ground and the neutral. And indeed, we have ground and neutral all connected together on this transmission line, much like we would have in a real one. And at the other end here, we have the same type of transformer. In this case, we're going to go from 10 kilovolts down to 120 volts and feed it in our lamp here. And we're going to look at the voltage that our lamp gets using this voltmeter, and we'll look at the voltage that's going into the transformer with this voltmeter over here. But it would be really interesting to see the voltage on our power line. And to do that, I made a resistive divider, which I'm going to attach to the power line. And I'm seeing here it's not quite long enough. Bear with me. This should do a bit better. Just using a little piece of copper wire to help us. So what is this resistive divider? Well, it is 50 mega ohms. I have 1, 2, 3, 4, 5, 10 mega ohm resistors in series over here, and I have a 20 and 30 kilo ohm resistor in series down here, so that the resistance between these 2 points is 50 kilo ohms. The resistance between these 2 points is 50 mega ohms. What that does is it does a 1,000 to 1 voltage division. So when this is 10 kilovolts, we should see about 10 volts at this point over here. And I think what we'll do is, since we don't really need to know what the voltage going into the transformer is, we're going to use this voltmeter to measure the voltage across our divider by attaching it across those two bottom resistors across the 50 k ohm section. And what we'll be able to do, I better get it one up. What we should be able to do is simply look at the voltage on that voltmeter over here, multiply it by 1,000, and that will tell us what the voltage is on the line. So let's try it and see what happens. Okay, here goes. And it worked. And we're getting about 9 volts, 9.3 volts across our voltage divider resistors. So we have 9,300 volts on our high voltage transmission line, and we're getting somewhere around 88 volts out of the step down transformer at the other end, and it is powering the light bulb quite nicely. Now we've lost a bit of voltage. We've lost about 25 volts, and that's probably partly due to losses in the transformers. Well, probably mostly due to losses in the transformers, because they're actually not designed for power transmission. They're designed for igniting propane and other gases and are inherently somewhat current limited. But what would be really interesting would be to see the voltage across our set of resistors, and for that matter also see what the current is in our high voltage line. So let's stop the experiment and add some more measuring instruments. So what I'm going to do is I made this ammeter that is fully self-contained and can hang on the wire here, and power will go in, or current will go in one terminal and out the other. And what I'm going to do is make a break in our power transmission line over here, and we'll insert an insulator, and then we'll hang this over there, and we'll be able to measure the current. So here goes. And the insulator we're going to use is this plastic thing that, well, is really meant to hold wires, and I was just looking for something small that I could use as an insulator. All right, there we have our hanging ammeter. And I should point out the markings on the ammeter show 0 to 100 because it was originally a meter showing percent of something, but it's actually 0 to 10 milliamps. And now I want to hang this hanging voltmeter across our line of resistors so we can get the voltage across them. And of course these things all have to be hanging because the voltage is so high that, well, we can't have them close to anywhere near anything that's grounded. And as I'm saying that, I'm looking at our voltage divider over here. I'm going to move that over a bit because we don't want a nice big arc occurring. And if you're interested in arcs, we did a nice video with arcs and sparks for Halloween, and we don't want to repeat that in this video. And incidentally, when I had it going a few minutes ago, when we did our first test, I could instantly start smelling the ozone, and for that matter, I could hear the corona discharge. All right, here we go. That's safely away from anything. That's safely away from anything. Let's see if we can see the current and the voltage across our 8K ohm resistors. Here goes. Let's see what happens. Our voltmeter that's hanging there is acting up quite a bit. It looks like the voltage is going up and down, but it's probably somewhere averaging out to be maybe 50, 60 volts, something like that. And our current seems to be Well, right in mid-scale, so somewhere around 5 milliamps. Well, 5 milliamps times 9,000 volts is somewhere around 45 watts, 50 watts, something like that. And if we look at our lamp getting 88 volts, it's probably consuming somewhere around that amount. Now, the interesting thing, and this is the first time I've done this experiment, is how that hanging voltmeter across our resistors is misbehaving. And the only thing I can think of is that it's the various coronas that are probably coming out from all around it that are messing it up, but I'm not really sure. But if we had 5 milliamps going through 8,000 ohms, we would expect to see somewhere around 40 volts across those resistors, and that seems to be the bottom end of the types of voltages that voltmeter is showing us. So even though that measurement's a bit wonky, this is a rather nice demonstration. So what can we see from this? Well, with the higher voltage, we have considerably less current flowing through the wire, and for that matter through the resistance that's in our 300 kilometers worth of wire. And the other thing is the voltage that is created along that resistance, along the wire. In other words, the voltage that is contributing to the lost power in the wire is actually insignificant compared to the total voltage on the power line. And so because it is insignificant to the total voltage on the power line, the amount of loss has become essentially insignificant. So we really have a double effect occurring. We have less voltage being developed across the resistive load on the line because it is a lower current, and even with that lower current, the voltage that it does create is less significant because the voltage is higher. So essentially, we have two effects occurring. We have lower voltage losses, and we also have a higher voltage making those losses even less significant, and therefore we end up having essentially a squared effect in terms of the gain we get by increasing the voltage. So in other words, in a very rough sense, if we double the voltage, we can cut the losses down by a factor of 4. Well, there's a demonstration of why we use high voltages for long distance power transmission. Now, we used 10 kilovolts, although it actually turned out to be a little over 9 kilovolts for our experiment. And you might be wondering, what type of voltages do we really see on the typical pole-mounted transformers? And in Canada and the US anyway, from what I understand, it's typically 4,000 or 8,000 or 12,000 volts that are on the power lines that supply those transformers. And there are indeed transformer substations that start off with a higher voltage and step it down to those 4 or 8 or 12 kilovolt type voltages. Indeed, there can be a number of layers going down from the long distance voltages to the home voltage. And the city of Ottawa has an electric company called Ottawa Hydro, and I'll put the link below, but they have a rather nice drawing showing power transmission from a hydroelectric power dam all the way to the home, first as it gets stepped up to increasingly high voltages. And interestingly enough, the maximum voltage going into Ottawa is a 500,000 kilovolt transmission line, And it turns out it wasn't actually that far away from where I lived. So I went out and took some video of it. It's kind of interesting. You can see a bit of ice on it. We had freezing rain the night before, and so the power lines got coated with ice, which shows you the type of loading, physical, mechanical loading, that power lines have to be designed for. And the thing that I thought was most interesting was just the size of those insulators. I mean, they're absolutely enormous. It would be really neat if we could have a person standing beside one of those insulators to give us a sense of size. But since we can't do that, it's sufficient to say, well, they are absolutely humongous. Now, the other interesting thing that you can see is each power line is, in fact, 4 wires connected together with some sort of a mechanical holding device. And you might be wondering why they've done that. Well, there's probably 2 reasons. And they all have to do with creating an effective diameter of the power transmission wire. If you have a very narrow wire, the electric field at the edge of the wire is much higher than if you have that same voltage on a much larger diameter wire. And the reason that's important is when you have a high voltage, you start getting electrons being stripped away from the atoms in the air immediately surrounding the wire, and that's called corona discharge. And in one of my previous videos, we looked at it and took some rather nice pictures of what corona discharge actually looks like, and it even has a sound. It has a fizzing sound. And indeed, when I did this experiment here with only 10,000 volts, I did hear the fizzing sound from the corona. In fact, I could even smell some ozone, which is a typical byproduct. And that is, of course, a source of loss. There's more corona when you have a higher voltage. And over a distance of 300 kilometers from here to Pickering, well, there's going to be a significant amount of energy that is lost due to corona. The other effect that we have to take account for is something called the skin depth. And essentially what skin depth is a result of the frequency of the power. In our case, 60 hertz, in other parts of the world, 50 hertz. And for 50 or 60 hertz, the skin depth is somewhere around 1 centimeter, give or take. And what that means is the bulk of the electricity flows on the outer 1 centimeter of the electrical conductor. So that also means that if you start making a conductor very thick to conduct much more current, well, the truth is the inside part of that conductor does not get used. And one of the ways to reduce that effect is to make the conductor look more like a pipe or something with a larger outer diameter. And so by having the 4 wires near each other like that, we can reduce the effect of the skin effect and probably get a lower resistance pathway by having 4 individual wires than one thicker wire where not much current flows through the center. So those are a couple of considerations that you have to take account besides just the resistance in the wire when you're dealing with high voltage, high current power transmission. When we are talking about the losses, in our little experiment here, I did a bit of a hand-waving discussion as to what the losses amount to and how, by stepping up the voltage, we can essentially reduce the losses by the step-up amount squared. So if we step up the voltage by 10 times, we can reduce the losses by a factor of 100. The other way to think about it is if we step up the voltage by a certain factor, like 10, what we also end up doing is reducing the current by a certain factor, 10. And if we reduce the current by a certain factor, well, the power lost in a resistor, the resistive effects of the wire, is given by a formula I squared R, so I, the current, squared times the resistance. So that I is squared. If we can reduce the current by a factor of 10, or whatever amount you've stepped up the voltage by, well, if we've reduced it by a factor of 10, that I squared squares that factor of 1 over 10, and once again we've reduced our losses by a factor of 10. So in terms of resistance, the higher a voltage, the better. However, there is a natural limit because of effects like corona. That sort of thing really limits the amount of voltage that we can put on the line before we just start losing a vast amount of power into the atmosphere. The other thing, of course, is the higher the voltage, the bigger we need for insulators, and that, of course, costs money, and the electrical engineers who make it their business to design long-distance power transmission lines are indeed experts at juggling all those factors to figure out what's the optimal voltage for a given amount of power to be transmitted a given distance. And when they get to even higher voltages, they switch to DC, because that makes more efficient use of the lines themselves, and we'll look at that at some future video. So that's the end of this video. I hope you found it interesting and useful, and see you next time.